My name is Jerry Quinn, and on behalf of the AFAA New England Board of Directors, I'd like to welcome you to our webinar. I'd like to thank our sponsors. First of all, our platinum sponsors, Fire Command Systems, J&M Brown Company, Mammoth Fire Alarms, Norel Service Company, Siemens Smart Infrastructure, Space Age Electronics, and our silver sponsor, TC Life Safety. Today's guest speaker is Gary Paul. He's the Regional Sales Manager for Protect-A-Wire Fire Systems, where he provides technical support to distribution partners for North America and Canada, as well as delivering educational trainings to the fire protection community. Gary has extensive experience working with engineers, project managers, and distribution partners. Prior to joining Protect-A-Wire, he worked in the wire and custom cable connector industry for 15 years. He's a member of the National Fire Protection Association and the Society of Fire Protection Engineers, and Gary holds a bachelor's degree from Stonehill College. So take it away, Gary.
All right, great. Well, I want to thank you all for giving me the opportunity to speak with you all today. We'll be spending the next 30 minutes or so kind of talking about the various aspects of NFPA 241, but from a manufacturer's perspective. I'm not going to sit here and tell you that I'm a code consultant or an expert in this area by any stretch of the imagination, but the information I'm going to try to present to you is gleaned from, the experts that are out there living this code, supporting it, expanding it, and bringing it to the conversation that we're having today. The truth be told, my first exposure to the NFPA 241 code was, literally a week before I started here at Protect-A-Wire. We had hosted a small group of individuals that had a facility that they had under renovation, and they were looking hard at different ways that they could protect their facilities during these construction phases, because typically, as you'll see and as we'll discuss later on, I mean, they have many of the systems that are available to them, but for certain reasons, these systems are taken offline to avoid false alarms and certain other things, which present some challenges to these job sites, going forward from a protection standpoint. So jumping right into the first slide, some of the challenges that we face here and things that I've learned in my conversations and my research myself is, who is it that owns the responsibility for these facilities? Is it the owner? Is it the general contractor? Is it the host of, subcontractors that are on here? And then next, we're talking about the alarm systems that are there, but they're deactivated. In other areas, we're talking about the composition of the construction that's taken place and some of the materials that are exposed and built up, whether it be in a trash bin or just materials being staged and ready for the next phase of the construction process itself. Then, of course, we're looking at on-site construction activities, hot works and welding and things of that nature. And then security always falls into it, because now you've got all your systems offline. So need a way to secure your facility so that you avoid arson and things of that nature. And this is a nice little saying that I took off one of the local contractor's site, for a presentation I did a few years ago. And it simply states that, safety is not about being compliant with laws and regulations that by themselves, will not keep workers safe, and at the end, it's basically safety is about people. And a little shout out to the Super Bowl 55 out here. It's not the kind of safety we're talking about, but, safety. It's on everybody's mind. So according to OSHA, just about every day, on average, 6.5 million construction workers show up to more than 250,000 job sites. That's a pretty staggering number. And if you start taking around the averages over 50 states, that's an average of 5,000 job sites per state. So that's an overwhelming number. You talk about the AHJs that have to monitor these locations, things of that nature. But these are numbers that are gleaned from the NFPA website, detailing some of the incidents that occurred during some of these construction processes. They've taken a couple different views on this, one stemming from time span of 2010 to 2014, and then the most recent one being published just this past year, covering the range of dates between 2013 and 2017. So we've got 2 5-year periods with a 1-year overlap in between. But as you can see, we're talking, in excess of 6,000 fires every year. And it's kind of interesting that the numbers, right off the bat, you see there's, consistency as far as the number of incidents, that happen. We also see consistencies in some of the civilian impacts that, occur on these job sites, whether it be, fatalities or injuries. But the thing that really kind of started drawing my attention was the amount of damage to these properties, in the millions of dollars between these 2 time periods, with the same number of incidences and same level of activity. We're seeing almost double rate of the number of damages that are being reported as a result. And I don't have any clear indication as to what the specific causes of these are. It could be a number of different things, but certainly with some of the advents in building materials and things of that nature, some of these could be leaning into it and just describing a more catastrophic scenario, if you will, as compared to what would have been seen even 5-10 years ago. And then we delve into the NFPA fact sheets themselves. So taking a look through these, this was kind of an interesting graphic that, again, shows up on the NFPA website just to support the number of fires. So just like any, typical Pareto chart, if anybody's done, root cause analysis or anything like that, first off, you want to take a look at, what is it that you're driving your statistics around? What is the, the number one thing that you're trying to, answer? And then from there, you kind of take a look at the cause and effect of what is contributing to the situation. So in this case, we're talking about fires on construction sites, renovation locations, and demolition sites. And so we're breaking it down into the various elements that contribute to the reasons why these occurrences happen. And to be honest with you, when I first started looking at this, about 5 years ago, it was kind of surprising to me, as a layman coming in from outside of the industry and kind of looking at all this stuff for the first time, that cooking equipment was top on the list for, sites under construction. Of course, I mean, now the number of, fires and, the resulting property damage that kind of ensued as a result, is kind of, night and day. It's the number one, cause in these situations, but it doesn't have quite the impact on the property damage. So it kind of leads you to believe that, that yes, they happen more frequently than anybody wants, but they're able to be, addressed quickly, and that the total impact on the construction site is, negligible, for lack of anything else. But then when we take a look at, further on down the chart in both structures under construction and in major renovations, you take a look at, electrical distribution, lighting equipment, and things of that nature that really kind of stand out and start driving the, kind of the lens and the magnifying glass into areas of concern, and kind of an area where you can spend most of your time, delving into what are the causes, what is it we need to do to, mitigate these areas so that these do not, present such a challenge as we move forward. And of course, this all leads to, what are we seeing in the news? And in this, we'll start right off with a fire that occurred just within the last week or so out in Las Vegas, Nevada. Many of you have already probably seen these, and you've probably seen many of the slides that I'm going to show here. But I'm going to go ahead and kind of illustrate what we're talking about here. Las Vegas, Nevada, as I mentioned, within the last couple of weeks, the cause is still under investigation, but we're talking about $25 to $30 million worth of damage to an apartment complex that was underway. And as NFPA today, cited in their headlines, massive fire at apartment complex under construction in Southwest Las Vegas reinforces the critical importance of NFPA 241. Notre Dame Cathedral, we're talking about, it's not just, local apartment, complexes and construction projects, but we're talking iconic structures. Here we have, the famous cathedral in Paris, France. This occurred just over a year ago. Over 400 firefighters are involved in this, and we're talking about damages and the estimate of 200 to 300 million euros. And of course, when you're considering the historical aspects of the artifact and the building and the structures that we're trying to protect here, there's really no value that you can put on, the significance of the loss of something like this. And of course, this was determined to be, one of the causes of the fire was determined to be faulty wiring. You consider the age of the facility, the age of the wiring, things of that nature, the structure of the building, old wood, so you've got basically a tinderbox that's ready to go up at any time if you're not careful and take the necessary precautions. Here in Massachusetts, we can cite a number of different incidents that, we've experienced over the years. In Waltham, Mass, back in 2017, another apartment complex, 10 alarm fire, 5 buildings were involved and engulfed. And they had fire alarms. Sprinklers were either incomplete or not in service at the time. But the big thing that they discovered here was that there was no NFPA 241 plan established when this project took off. South Weymouth, Mass. I'm not sure if anybody's aware of or familiar with the Naval Air Station in South Weymouth, but that's been an ongoing development project for the past, God knows, 20 years, 25 years, as long as I can remember. But it's been, a constant battle. We've had more than, our fair share of construction projects in here, building owners and starts and stops. But this was a 50-unit condo complex that was a week away from commissioning. They had all the life safety equipment installed. They had sprinklers in place. They had smoke detectors in place. And then next thing you know, fire breaks out and none of the systems are are active, to be able to respond to these incidences. And as a result, you have $20 to $30 million worth of damage. And of course, this one was determined to be arson. And then out in Overland Park, Kansas, similar, hot works was being performed on an apartment building out there, $25 million worth of damage. And, and that I highlight this one little sentence at the bottom of the paragraph there, because as we look at NFPA 241 and what it entails as far as, providing good housekeeping and instructions for how to safeguard, these construction sites. The other aspect that we're concerned about when we're talking about these safety measures is not only the structure that we're working on, or the building that we're renovating or demolitioning, but we're also concerned about the impact that the sparks from these massive fires are having on the community at large. A lot of times these sparks are flying anywhere from a couple of 100 yards to several blocks away and impacting local businesses, local family residences, things of that nature. So it's not just an isolated concern within the constructs of the actual construction site, but a more broad conversation and protecting everybody around it as well. And again, Santa Clara, California, just to illustrate the point, 4-alarm fire, 56-unit apartment complex, 20 million plus or minus in damages. And again, we're looking at hot works and a great big tinderbox that just, once it gets going, seems to take on a life of its own. So one of the things that we're starting to see in some of these construction projects is the advent of engineered lumber. Now, with all material sciences, we're going to see advances in making things lighter, stronger, faster, more resistant to rot, more resistant to, whatever you have it. So here, according to the American Wood Council, some of the recent advances in building materials, well, we're seeing 7-story wood frame structures that are now withstanding 7.5 magnitude simulated earthquakes. And as it's noted there, with almost no cosmetic damage. It's not to say that there's none, but it's still pretty amazing that you have a 7-story building that's able to withstand something of such calamity. Other things that we're seeing are, they're starting to pass FEMA wind tests for safe room requirements, which, entails a 250-mile-an-hour wind test. And not only that, but also 100-mile-an-hour missile tests, and these guys are meeting the requirements to develop wood structures for these purposes. And then there's a nice note there in California. California estimates that they have 400 million square feet of public schools, and 80% of that is wood framed. So that equates to about 320 million square feet of wood construction that's housing, the brightest young minds of our country. It's a cause for concern, especially if there's any renovation projects that are going on, which typically these are typically in flux to advance and build to the latest building codes or meet the demands of whatever the community needs as far as added rooms, new technologies, things of that nature. And of course, with the advent of all these material advances, what we're starting to see is timber is reaching new heights. We've got stronger materials, so these materials, comparatively speaking to, typical construction of, steel and concrete, they're representing a lower material costs. As far as material costs and everything else is concerned, now we're able to build. Construction times are, increasing. Their construction times are actually 25% quicker, which, can constitute a reduction in traffic, which, was a fact that I gleaned from the American Wood Council when putting this together. But I think the biggest nugget to take away from this particular graphic and this this development, as far as stronger materials and things of that nature, is that the 2021 version of the International Building Code has now introduced 3 new construction types into their into the actual code, and it's actually allowing for wood construction up to 18 stories, which at one point in time it was unheard of. 4 to 6 stories was unheard of and a major cause for concern. But now, as you can see, we're looking at 6, 9, 12, 18 stories in a single building, and it's kind of the graphics represent in the previous slides. What we're looking at are, basically tinderboxes. There are advances that they're making as far as, fire ratings in these materials, looking at 3-hour fire ratings, but there's a big controversy over who's got the responsibility to design these into the plans. Is it the structural engineer? Is it the architect? So there's still some work to be done behind the scenes, as we forge forward in these larger and more unique structures to be able to address, the real fire hazards that they present, as you can see here. Once they get going, it's a tinderbox. So what is NFPA 241? The safeguarding, construction, alteration, and demolition operations. The code was established back in 1938, so that was right around the time that a little-known manufacturing company came up with an idea for a new detection device. Truth be told, that was protector wire. We started back in 1938, right around the same time that this code was initiated. It was last revised back in 2019, and some of the things that it delves into is, who's responsible. what are the involvement levels of the various individuals on these sites, the property owners, general contractors, folks of that nature. It assigns a full-time fire prevention program manager and also requires the development of a plan. So what is this plan and what does it entail? So the plan development, basically, focuses around an executive summary. It's going to list all the hazardous operations that you have on site. It's going to detail the features of the fire protection plan. What are some of the, apparatus on site that are going to be used, whether or not you have, handheld extinguishers. Do you have, any kind of ancillary detection methods out there? Logs and inspection forms for any hazardous operations that are being conducted to make sure that you have the proper permitting and you've taken all the necessary precautions to protect against those. Any impairments that might be had on the site, and also what a typical floor plan on this facility is going to look like, so that as first responders come to battle the blaze, they know what they're dealing with. They know the size, the basic volume of the structure, and where these hazards lie. And we're starting to see the conversation grow and grow around NFPA 241 as these numbers and these fires, become more and more mainstay in today's news cycles. We're starting to see the development of NFPA 241 in other codes. NFPA 1, Chapter 16 states that all structures undergoing construction, alteration, or demolition will comply with 241. The International Fire Code also has adopted NFPA 241 in their Chapter 33 covering fire safety during construction. And it defers to 241 for items that aren't currently addressed by the chapter itself. And similarly with the International Building Code, same chapter, Chapter 33, safeguarding during construction. NFPA 241, by way of the International Fire Code, references this code to make sure that anything that's not directly addressed will be addressed through this form. So the conversation's increasing, and it's kind of interesting. Being on the manufacturer side, I've got distribution partners throughout the country that I talk to and I present to on a regular basis, and in by and large, local enforcement are the people that are going to really kind of drive the bus on these things. Code is good. Or is going to be as good as how well it's enforced and how much people know about it to really kind of take it to the next level. Here in the Northeast, by far, the conversation has been strong for a great many years. As I said, when I first walked in through the doors, it was one of the first conversations we had, and it was with one of the local companies. We also had one of the local contracting firms come down and speak to us about different methods that may be available to them to help mitigate some of these fires and, at least provide some asset protection during these construction phases, and especially in cases where you have, a fire panel on site or suppression or anything like that, but they've been turned off. But you still need to have some sort of awareness of what's going on. And there seems to be a whole industry of different solutions popping up all over the place, from wireless detection devices to, smoke alarms and fire detectors, flame detectors that will, radio out and keep watch on these places. But truly, here in the Northeast, and we have to give a shout out to the Boston Fire Department, because I really believe in some of the conversations and some of the seminars that I've been to, they've been the most vocal, and one person in particular, throughout my travels. In fact, I've run into them in more than one region of the country, talking specifically to the local chapters of whether it be SFPE, local AHJ gatherings, things of that nature, just to kind of highlight NFPA 241, that it's there, that it's available, and that, it is enforceable, and that there are ways to, start mitigating some of these problems so that we can kind of continue pushing out that conversation forward. As you can see, this is taken straight from the City of Boston website under fire inspections and temporary construction. And here they're just saying, it's understood that, smoke or heat detectors are frequently utilized. And here are some of the requirements we'd like to see when reviewing the system, and they kind of go out to spell that out a little bit. They don't name anything. They don't give specific recommendations, but the fact that there are other things that, we should or could be thinking about to kind of advance the conversation anyways. And as I was mentioning, my exposure throughout the country kind of gives me a unique view of the different marketplaces and, where the conversations are strongest, where, really NFPA 241 is not even a blip on their radar. And it's kind of interesting because you do see the varying degrees of awareness and enforcement going on. And I don't think it's for lack of caring or trying. I think in most cases it's either misunderstanding or it's just bandwidth. As I mentioned, I mean, when you're talking about the number of construction site projects that are undergoing on any given year, that's an overwhelming number, and it taxes the local resources to be able to keep up with all these projects to make sure that they're doing what they're supposed to be doing. So NFPA 241 kind of puts the onus back on the building owners, back on the general contractors to kind of establish these plans so that they're going off and taking the best position they can to mitigate any potential catastrophes. And here in California, one of the things that we saw, and this is, this just kind of came across our radar in the last 4 or 5 months, unbeknownst to us, California Fire Code had actually adopted a section 3308.5. And in it, they state that any wood construction projects exceeding 3 stories in height shall be provided with a listed fire alarm system and provided with linear heat detection during construction. That's a very interesting concept. Great for folks that are manufacturing linear heat because it's kind of where we play. These special hazards, present a unique challenge, and within these unique special hazard applications, we find that linear heat is kind of like that niche element that tends to find its way into these areas, especially given its construction, its ease of use, its simplicity in testing, things of that nature. So it's a viable option out there that we're starting to see become more and more mainstream. So what is linear heat? Linear heat detection is, it's a unique cable that detects heat conditions similar to a spot heat detector, and it will do it anywhere along its entire length. So it looks like a piece of fire alarm cable. The construction, the manner it's manufactured is identical to the way that a typical cable would be manufactured, whether it be fire alarm cable, Cat 5, Cat 6, or even THHN. So we go through an extrusion process. We have heat-sensitive polymers. Big difference here is that this is categorized as a device. Even though it looks like a piece of wire, there are some nuances to it that allow it to operate in these unique applications. We've been categorized as a digital contact device, and we've been FM and UL approved since the 1940s. Now, as a digital device, what we're talking about here is binary. And quite literally, we're talking, digital in the true sense, ones and zeros. So in its state, it's a normally open contact, and all we're looking for is a contact closure. So quite literally, the device is either on or it's off. So some of the features and benefits of unit, it's ease of installation, as I was mentioning. We're talking about a continuous run of linear heat that anywhere along its length, it's able to sense heat events going on and short out to send a signal back to an alarm panel. How it then conveys back out to the general contractors or the foreman or the fire department is up to the panel that it's being supervised by. But the nice thing about it is that it can be applied into a variety of different environments, you know, caustic environments, heavy wet conditions, cold conditions, hot conditions. It can be placed very close to the actual proximity of the hazard that we're trying to protect. In some cases, we've seen linear heat being applied directly to the surface of some of the applications that we see, such as, you know, transformers or conveyor belts, things of that nature. It does have a fast response and a very long service life. Given the steel core conductors, there's very little that can actually cut through these things. In fact, we always advise anybody that's done any work on these, you know, make sure you have a nice heavy duty pair of wire cutters, because your normal wire cutters that you use for, you know, cutting through copper is just going to be, you know, it's going to bite the dust very quickly. So within the linear heat detection family, we have a number of different options available to us. You know, back in the beginning, PHSC up in the upper left-hand corner, that's kind of where linear heat got its start. That is the product that most are familiar with when they hear linear heat detection or when they hear the name protector wire. Basically a two core conductors construction, two steel core conductors wrapped and encapsulated in heat-sensitive polymer, and then we have an outer jacket on there for environmental concerns. Really, the magic happens here is with the heat-sensitive polymers. Those are all fixed temperature devices that are specifically designed to melt away and expose the conductors at a very specific activation temperature. And these follow the norms, you know, as you see in most other applications for fixed temperature, 155, 190, 220, and so on. PLR takes the same basic concept. Big difference between the two of these is we add an element of copper to the outer conductor to reduce the overall resistance value of the inherent steel that is used in the construction. Steel has a resistance value of about 0.185 ohms per foot. So when tying off of others' equipment, the IDC is going to dictate, and the output capabilities of the IDC is going to dictate how much linear heat you can actually support off a single module. By adding copper, we reduce that resistance value, and by reducing that resistance value, we can actually increase the amount of detector that we can support. So with steel having a resistance value of about 0.185 ohms per foot, copper reduces that by 2/3. So now what could be, you know, a 500-foot, you know, zone suddenly expands to almost 1,500 feet. Fiber optic is probably the latest and greatest, and probably the future of linear heat with respect to true capabilities and ability to provide real-time information on what is going on throughout your zone. Typically, linear heat is a fixed device. It's passive. It doesn't know whether or not it's an actual heat event until those heat-sensitive polymers melt away. So it doesn't have a lot of capabilities as far as knowing whether or not you have a fire going on, or if, you know, someone suddenly hit it with a 2x4. With fiber optic, we take it's a sharp left turn from our passive device, and now we have an active device. So because we're pulsing a beam of light down the length of the fiber and reading the array of backscattered light coming back, we're looking at two specific frequency bands to be able to determine at any given time and any length along the fiber what the physical temperature is going on. So think of it as almost like a thermometer running throughout your facility. And at any given time, you know exactly what the temperature is. So now through software and through the interface module, we can program into the unit a variety of different activation requirements. So not only can we, program this for fixed temperature, but we can also program it for rate of rise. We can have rate of rise and fixed temperature being, reviewed simultaneously. We can program it for deviation from zone. So if you're typically seeing 72-degree ambient temperatures throughout your zone, and then all of a sudden you see an anomaly where it's, deviated up to 95 degrees suddenly, not only are you taking into account rate of rise, but now you've got a deviation from what your zone typically is, and you can program the system to bring attention to this. Not only that, but we're also seeing applications in larger projects, like tunnels and things of that nature, where they're actively monitoring the fiber unit and the information that's provided in a real-time basis, and feeding that into other control equipments for HVAC, for instance. So in tunnels, as temperatures rise and traffic increases, you want to increase airflow. So now the HVAC systems can glean whatever information they can off of this unit, and then determine whether or not they need to open up vents and turn on fans to increase air circulation. If there's a true heat event there, they've got CCTV cameras that are trained to turn to the spot of the fire immediately, so the guys in the control room can actually see physically what's going on. They know where it's happening, and they know what kind of an incident that they're dealing with. So as they advise and call out to the fire department, they can tell them where the fire is, what kind of fire, what direction it's traveling in, so they know the best way to combat this, and they're prepared before they even jump in their trucks as to what to expect when they get onto the site. For today's conversation, CTI is going to take front and center, though. And CTI's got some unique characteristics that kind of lend itself to applications such as NFPA 241, and why we're seeing it being adopted so widely. As I was mentioning before, excuse me. There we go. So within the digital linear heat detection, this is a typical operation. As I was mentioning before, we're looking at nothing more than a contact device. And it's a fixed temperature device, and we know that it's either on or it's off. So in its typical state, in our number one position here under conditions, we see a normal green interface module. We see the line condition with an end-line resistor, and we're simply waiting for those heat-sensitive polymers to melt away to bring those conductors into contact and short out the system. We can determine if one of those conductors has been cut and register an open. But by and large, we're waiting for those conductors to come down, close out, short out, and then initiate the sequence of events that's going to take place afterwards. With CTI, we've enhanced the design and taken the basic concept. As you can see, the construction is identical. We still have our two primary conductors. We still have our heat-sensitive polymers. We're still wrapping the construction in a polymer tape to hold that construction tight together so that they don't move anywhere, and they're in close proximity to each other to react as quickly as possible. Still have our outer jacket that is, there primarily for environmental concerns. We have a regular PVC jacket that's good for light industrial indoor applications. We have a Teflon jacket that is more suited for outdoor harsh conditions, UV resistance. It resists many of the caustic chemicals in most of the industrial applications. We have seen a few that it doesn't address. So for those, we've had to come up with some specific formulations for those applications in particular. But by and large, we've found that the majority of applications will withstand, the FEP jacket will withstand the majority of the applications out there. But the nice thing about this is that even though we're looking at the same basic construction principle, there's one element that we've changed that radically alters the way that this system functions out in the marketplace. And that is the two basic core conductors that we're using. Instead of two steel spring conductors, as we've been traditionally using for the past 80 some odd years, we've changed things up, and we went with a combination of Constantan and a copper-coated spring steel conductor. Now, between copper and constantan, we're looking at two dissimilar metals. And what these dissimilar metals do, and before I even go beyond that, what we're looking at here, for those that are familiar with thermocouple principles or thermocouple technology, we're looking at here is a type T thermocouple. So what happens is with the type T thermocouple, or with any thermocouple by that matter, two dissimilar metals, when they come into contact with each other, there's a natural phenomenon that occurs where they actually emit a microvolt of electricity, upon their contact. And with the type T thermocouple, what's been discovered is that as temperatures rise and decrease, that the level of microvolts being emitted will actually increase and decrease in direct correlation with that temperature. So now that we know what that function is, we can take that information and apply it to a standard linear heat detection. So whereas before, if we have these two conductors and suddenly we have an active facility, and someone runs into it with a forklift or hits it with a hammer on a construction site, as opposed to going straight into alarm, evacuating the site, setting off sprinklers, calling the fire department, we now have a system that through the interface module, we can actually interpret what's going on. First sense is to determine that we actually have a fault. Second is going to be where is that fault, and then the third is to actually interpret the temperature at that location and compare it to a pre-programmed initiation temperature. So if the conditions in the area are measuring ambient conditions, say 72 degrees, 65 degrees, whatever it may be, but you have an activation of requirement of 155 degrees, you're not going to have false alarms. This is going to have enough intelligence built into it to know that it's not a heat event that's causing it to go into a fault. It's actually somebody or something that's come in contact with it that's damaged the area where the conductors came into contact, and will alert you to that scenario. So through the interface module, as was mentioned, we can do either a Class A or a Class B. So with CTI and being a thermocouple type construction, polarity is imperative, and it is required that we put everything through this interface module. The interface module acts as the brain of the system. So the detector is still a digital contact device. It's still a fixed temperature device. So they're offered in the same array of fixed temperature offerings that all the other detectors are available in, 155, 190, and so on. The big difference here is that with the interface module, once we see the short occur, we can take these temperature measurements and apply some logic to what's going on in the field to determine whether or not we actually have to raise the alarm. So as I was mentioned, this can be configured in a Class A or Class B, and we can support up to 4,000 linear feet. One of the things I always try to warn people on this is that introducing an additional type of metal into the thermocouple construction will actually have some adverse reactions to the electricity flow, to the level of microvolts that we're trying to measure at the spot of these faults. As I was mentioning before, we had very specific resistance values within copper and constantan, things of that nature. You start adding in copper feed cable to the equation, and now your numbers are going to start getting skewed. So we always, caution anybody if they're choosing to use one of these systems to, keep that in mind as they lay out their plans. So similar to our fixed temperature devices in the legacy products, our PHSC, our PLR, we can still register an open fault. So we know if one of the conductors has been, damaged or cut, and this is typically a true cut. Someone hit it with a pair of wire cutters or something like that. And typically what you're going to see are, both conductors cut. But the nice thing about it here is what we can actually determine a short fault at the spot of where the fault occurs. Through alarm point metering, we can tell you where that fault is. And then the last operation is now we're taking an actual temperature measurement there. That temperature measurement is then compared into the interface module on the fixed temperature profile that's pre-programmed in there. All you have to do is, as you're installing and selecting, there's a back menu that gives you the options to select 155, 190, 220 is your initiation temperature. Now the system's ready to understand what it is that you have installed. So if you're installing a 155 detector, you program the system for 155-degree activation. So now if you have a fault, the system's going to take that temperature profile and compare it to what's been programmed into the module, and then make its decision based on the initiation criteria. If it stays in a ambient conditions and well below the activation temperature, it stays in a fault condition. Tells you where out in the field that the fault has occurred. You can go out, splice out the damaged section of the detector, splicing a new section, and reactivate the system. The nice thing about this, in a Class B configuration, we actually have active detection ongoing up to and including the spot of the fault. In a Class B configuration, the only area that you typically lose in these scenarios is from the spot, from just beyond the spot of the fault out to the end-of-line resistor. That becomes your dead zone. But in the Class A configuration, because we're taking bidirectional measurements and monitoring the system in two different directions, we can actually maintain full integrity of the system. Unless you have two faults in two different locations, then that area between the two faults becomes your dead zone. And that's just in the Class A configuration. And that's just another illustration of what I'm talking about. So here in a Class B, you've got your extension grade. These are your feed cable. This is special feed cable that we offer to work directly with the detector. But then you have your start of your detection run, and then you're ending out in the field with the end of line resistor. So as mentioned, with a Class A, we're going out. We're still covering the area, the zone with the linear heat detection, and then coming back out and back to the module with the extension feed cable. But we're still measuring bidirectionally, so you typically have full coverage even in a fault condition. So as we start looking at applying this within construction and renovation projects, we're simply looking at going up and down hallways and in and out of rooms typically to provide the coverage that's needed and the detection requirements that are sought after in some of these applications. This is an example of one of the building plans that we saw recently that they're planning on just going in with linear heat up and down the hallways and in and out of these particular storage rooms and what have you. The nice thing about it is that, similar to a spot heat detector, linear heat carries the same open area listed spacing. So spot heat detectors and linear heat both share 50-foot listed spacing based, on NFPA codes, is based on a 10-foot high ceiling, and then derated for however high the facility is. But in most cases, in a renovation projects, drop ceilings, things of that nature, you'll see this run up and down the hallway. And I've got some examples of that in the next couple slides. This is just another illustration of the same concept of how the linear heat can come in and protect the facility during these renovation and construction projects. And here's what we're talking about: temporary protection, in a classic dorm room setting. Here the renovations are ongoing. As you can see, we've got detectors that have been taken offline. In fact, we've got them all, wire nutted and isolated. We've got, temporary lighting strung up and down the hallway. But as you can see, the red cable coming in and out of the rooms here, that's the linear heat detection. So then we got continuous coverage, throughout the facility, and we can sense these heat changes or a heat event anywhere along its length. So as opposed to strategically locating these 50 feet, 50 feet, 50 feet. Now you've got what would entail is being double coverage just for the sheer number of loops that you're going through, the height of the area you're going into, and things of that nature. And the nice thing about linear heat detection and with the interface module through dry contacts, we are compatible with any fire alarm control panel out there. So if you have an existing system on site that's just been deactivated because of the work that's going on, you can tie this module into that panel and program it to do whatever reporting sequence you want, whether it's just to be dialing out to make notification to the people that need to know, or the fire department, or even if you just wanted to have an outside horn that goes off to clear the construction site. As you can see, we're talking about exposed runs here within these facilities. We got service loops to be able to extend off into other parts as the project expands and becomes more involved in different sections of the building. And more fun. These are university dorm rooms, I believe, in and around the Boston area. We've seen some from out in the California market. We're starting to see some from out in the Midwest. I know Kansas City's been looking hard into different technologies to help safeguard some of these sites. So this is the information that we share around to show, what are some of the applications and some of the techniques that are being employed in and around these parts. And again, I mean, we're just zip tying these directly, zip tying to them, perfectly, legitimate. One of the things we want to caution in, typically applications like this is you don't ever want to over tighten these to the pipes. The polymers that are separating these conductors are sensitive. I always liken it to kind of like a candle wax. Like a candle wax, it's designed to melt and give away as heat approaches it. So being something in that line, if you start applying undue forces and undue stress and strain around these conductors, you can start to splay out those heat-sensitive polymers, and you may not have a false alarm or a fault, immediately, but it's just a matter of time, given activities and things of that nature, when those polymers will start separating and you will bring those conductors into contact with each other. So we always, look for, in some of these applications, nice loose bindings around, especially in an application like this where it's going to be temporary detection. The word temporary is exactly that. You want this up here for a fixed period of time, and then you want to take it down. Now, if this were a permanent installation, we might have some comments to say about, some of the methods that are used to support the detector through these facilities, but it's not. They're looking for easy ways to get it up quickly, so that it's effective and in close proximity to where it needs to be. But at the same time, they want to be able to know that, at the end of the job, they can easily take this material down without a lot of aggravation, without a lot of, fanfare, and be able to move on to the next project. And this is a classic example. I mean, here we have an existing fire alarm panel. We've got the CTM 530 interface module tied directly into that fire panel through the Form C contacts, and then we're running straight out with the detector into the zone. So this is just a good example of how one company has decided to adopt, linear heat to remedy some of their on-site challenges. And that just about wraps up everything for the for this. I'm seeing some questions pop up here, and so Guys, didn't know if you want to kind of open this up for conversation. I see one question here I can address right off the bat.
Yeah, absolutely, Gary. If you could just jump right in and people can chime in with questions.
Sure. So I've got the question here. Do the cable ties fail prior to activation? I'm not really quite sure what the basis or what the meaning behind that as far as failing.
So Gary, I think what he's getting at is that the cable will fall off of the ceiling if the cable tie melts.
Oh, I see what you're saying. Well, these are nylon 6. They are a higher rated material, so they have a higher melt temperature than you would see out of the activation temperatures for these detectors. As I was saying, I mean, we range anywhere from 135 degrees Fahrenheit all the way up to 500 degrees Fahrenheit. And we have all the common intervals in between. So at 155 degrees, we're still below many of the melt temperatures of some of these products. So the detector, all depending on how fast and how involved the fire gets during the process will determine whether or not it's still there. But at that point, your alarm's going to be going off regardless.
Right. And do you see the other questions coming in, Gary?
I do. I see one here coming in. Since Protect Wire is listed as a device, it's not plenum rated and therefore needs to be removed at the end of project for temporary applications. Correct. It's a common debate on the plenum rating and how linear heat detection falls in with the typical plenum requirements when it comes to wire and cable. Truth be told, my background, I spent 7 or 8 years in wire distribution, and I've dealt a lot with plenum cables, riser cables, especially in the fire alarms category cables and things of that nature. And I understand the premise of the question. One of the big questions here, though, is technically, even though we look like a wire device, and looks like we should be conforming to the same requirements that a wire would need, we are technically classified as a device. So the big question comes to our spot heat detectors plenum rated or required to be plenum rated? And that's usually the conversation. We have looked into offering a plenum rating just to satisfy the questions that we get on a regular basis. But so far, I've not had any direct incident where anybody was not able to leave it. In fact, we're starting to see applications where, particularly out in the California market, and I think we're starting to see some activity here in the East Coast, is that they're looking for heat detection up in the drop ceiling areas below, that is, above the sprinkler area, but so that they have some method of detection. Now, technically, anything that goes up into these areas has to be plenum rated, but yet we're starting to see linear heat being adopted into these areas. So it's a semantics thing, and it comes down to how is the product classified and what its intended use is designed for. I hope that answered your question. Yeah, so in a permanent installation, is there a listed fastener to attach the wire? Yes. So all depending on what type of an installation you're looking at, what kind of support equipment that you have available to you. There are a myriad of different support pieces that we've gone out, we've evaluated, and we've even come up with and designed our own to work best with these detectors. Because as I was mentioning in some of the slides before, and you notice that the big open tie wraps were nice and loose and didn't over cinch the detector. Having the device snugly fit around the detector is ideal. So if you're attaching directly to the sprinkler pipe, we have double loop pipe straps that will, allow you to cinch very tightly to the pipe itself, but then it provides a second loop in there to gently support the detector and provide a more permanent long-term installation solution. And now I know in some codes, the interpretation of, whether or not a, something that looks like a piece of wire can be hung from a sprinkler pipe. There's certain interpretations that nothing can be hung from the pipe, but there's also interpretation that true to the spec, and I believe it's FMA-29 states that nothing should be hung to the sprinkler pipe, and I'm paraphrasing here. Nothing should be hung from the sprinkler pipe that's not integral to the operation of the sprinkler. Well, in that argument, we look at linear heat detection being the pre-action that initiates the response from the sprinklers. It could be a double interlock pre-action type system where you have a dry pipe and you're releasing air and waiting for the heads to pop, things of that nature. If that's the case, then yes, the linear heat detection is typically integral to that application. But it always boils down to AHJ interpretation of the code, and at the end of the day, it's going to be AHJ that makes that determination. But we do have others, depending on the situation. We have stainless steel for caustic environments. We have beam clamps. We have plastic connectors, but all designed to provide the long-term support you're looking for. In food manufacturing environment, cable ties often require metal core. And yes, we have seen this, and we have started to do some initial research into what we can do. We've seen some new tie wraps that are being presented out there. I think out in New York State, we've seen a number of requirements out there where food service manufacturers are replacing any plastic tie wraps anywhere, whether it be attaching category cable or linear heat, in replacing these with the metal core. We are looking into that. We haven't come up with anything yet, but it is something that's on our radar screen. All right, these questions are coming in pretty quick.
Good questions here. We'll probably cut it off after this one, I think, in the interest of honoring our schedule. But
I don't have a clock on here. So what time do we have? A little after 1. I apologize.
That's all right.
All right. So I'll take these last 2 questions. This one looks pretty quick. What is the wire distance limitations off the CTM module? So the limitation is 4,000 linear feet, and as I was mentioned, and because we're dealing with a Type T thermocouple, we can't use any copper feed. Typically, in historical fashion, protector wire can be tied into linear heat, and you can put on just about as much, copper feed cable, and you can put as much on there to support your installation, whether it be 500 feet or 5,000 feet, and not impact the zone coverage of a typical system. With CTM, because we're dealing with the Type T thermocouple and the resistance values inherent within those 2 conductors, and the fact that we can't introduce copper into the equation, we have to use an extension grade Type T thermocouple. So that's where our limitation gets capped at 4,000 linear feet off the module. And then, can protector wire be connected directly to any fire alarm control panel IDC zone module, or do you need to use the interface module to maintain listings? So it all depends on which detector you're using. So with the CTI detector, the CTM 530 is required, and it's the only detector besides our fiber optic that requires the interface module. And the primary reason for that is it's the brain of the system that's giving you all the information as far as false alarm discrimination and knowing what the temperature is going on to know whether or not to react. As far as our legacy product, PHSC PLR, these are just contact devices that can be supported by copper feed cable and can tie into anyone's equipment with or without interface equipment. Now, the big question then becomes, what is the output value of that IDC that's supporting and supervising the linear heat? And that's where we get into, how much resistance value the IDC can support. And then we get into the resistance value of the detector. And then we start doing some math to tell you. So long story short, a 25 to 50 ohm IDC with a 25 to 50 ohm output IDC will support anywhere from 250 to 300 feet. I know there's some modules out there that range up as high as 1,500 ohms that, can support up to 8,000 linear feet. So there's always a question comes down to that IDC. And if there's ever any questions, feel free to reach out to me. Happy to go over and kind of touch base on those.
All right. Well, Gary, thank you very much. You can tell from all the questions that people were engaged and interested in the product. So appreciate everyone's attention. And if you have colleagues who'd like to see this session, it'll be posted the next couple of days out at AFAA-NewEngland.org. So feel free to direct them there. So thanks again, Gary, and thanks to everyone for attending.
All right. Have a great afternoon, everyone. Thank you.
Yep. Thanks. Take care.